One final rule that I forgot to mention earlier is that when we integrate an exponential function with base other than e, we get this little correction factor, natural log of b. And I hope that you recall when we differentiate a function b to the x, the derivative with respect to x of b to the x is natural log of b times b to the x. And so when you differentiate, that little correction factor is a numerator sort of thing. When you integrate, that correction factor is a denominator sort of thing. If you remember this one, you can recover this one. So a couple of examples, and I want to show you both of them at the same time, and I want to compare these two examples because they're similar in some ways. So, of course, their limits are different. These are both different definite integrals. I believe this is number 7, and this is number 8. These are both definite integrals, and they're similar looking, and the only difference that you can see, or that I can see, is that this one has an x in the numerator. This one doesn't. So if you're comparing, let me bring back our inverse trig rules. If you're comparing the top integral, it looks just like, let's see if you can see this. Nope. It looks just like the rule for inverse tangent. Right? It's basically the same, except the inverse tangent rule that I have written here has the dx out to the side. When we have a numerator of 1, very often you can write the dx out to the side, or most often in print, like in Rogowski, you'll see that dx in the numerator. So that's just the differential dx, and they're just essentially multiplying it by that 1 in the numerator. So this one is textbook problem, right? I mean, I have integral 1 over 1 plus x squared. That's what I have. Here's my antiderivative, and I just have to employ a different technique to evaluate the definite integral. This one would be inverse tangent of x. Here's the way I denote a definite integral. I think our book just writes a vertical line here and writes the limit of integration. So that's inverse tangent of square root of 3, evaluated at the right-hand endpoint, minus inverse tangent of 1, evaluated at the left-hand endpoint. And if you want to see a little bit of trig, where that comes from, I'm thinking of this trig ratio. Remember, inverse trig functions take in ratios and spit out angles. This trig ratio comes from this sine ratio and this cosine ratio. That's one place we can get it. And so without needing to drag out a calculator, for what angle from minus pi over 2 to pi over 2 is root 3 over 2, the sine ratio, and 1 over 2 is the cosine ratio, and I believe that's pi over 3. And where is the tangent ratio 1? Well, where sine and cosine agree, and I believe that's pi over 4. Get a common denominator. I'm going to let you guys do that. And you end up with pi over 12 as your final answer. So what's different now about this second example? When we see this right here, we might be tempted to grab for those inverse trig function formulas, but this is not exactly like those inverse trig functions. Some things we can handle, this kind of thing we can't. So what we can notice that we need to do here is, if this were my u in a u substitution, like say u is equal to x squared plus 1, then what's du? Well, I take the derivative of this with respect to x, 2x, differential is dx. So I almost have, if this were u, I almost have du. There's x dx. I just need a 2 there. And I want to show you a way that you can handle this. You can either say, I would have du exactly if I put a 2 here and corrected my broken equality by putting a 1/2 on the outside of the integral, right? So I've not changed the integral. I've got 1/2 times 2. Or another technique would be to solve for dx and substitute. So dx is equal to du over 2x. Whoops, solve for this stuff right here. x dx is equal to du over 2. Taking this guy right here, x dx, and solving for that. So then I can make that substitution. All right, so here's our substitution. Let's see if you can see all of this. X dx is, oops, I'll fix those in just a second, is du over 2. And what's down here in the bottom? That's u. So now what about my limits of integration? Well, here my variable of integration is x, and as x varies from 2 to 7, we're accumulating area. Well, now my variable of integration is u. As u varies from what to what, am I accumulating area? Well, we've got to figure this out, and this is reminiscent of the lab that we assigned this week. If x is 2, u is 2 squared plus 1, which is 5. If x is 7, that other limit of integration, and then I'm coming here for my substitution of u is equal to 7 squared plus 1, which is 50. So those are my new limits of integration. As x goes from 2 to 7, as x goes from 2 to 7, u goes from 5 to 50. So I got to change those limits of integration. And now I can just integrate. Okay, so this is equal to 1/2 integral 5 to 50 du over u. And do you recognize that form? That's the one that is the natural log of u. And I'm just transferring that 1/2 out front. My limits of integration, 5 to 50. And so this is 1/2 times natural log of 50 minus natural log of 5. Using my logarithm properties, I get 1/2 natural log of 50 over 5, which reduces to 10. That's 1/2 natural log of 10. Review your logarithm properties to see how we get to this last step. All right, that's just 10 to the 1/2, and I did the power rule to float that up top.